when we talked about the kinetic molecular theory, we talked about an average kinetic energy of molecules. So in order to really understand that aspect, we need to look at distributions of molecular speed. So what we can say about this is that molecules at any instant have a wide range of speeds. And we can show this graphically by plotting on the y-axis our fraction of molecules with a particular speed, and on the x-axis the speed. And typically this would be in meters per second. So if we look at this graph, we will see something that kind of looks like this. And we can say that, or we can come up with a value here that will represent with a u, where u is going to equal the root mean square speed. So all of these molecules have various speeds, but we can refer to a root mean square speed of these molecules, and it's kind of similar to an average. So this initial plot we did right here would be at 0 degrees Celsius. But if we took the same molecules and heated them up, we would see a shift in our graph. And that shift is going to look something like this. So this is at 100 degrees Celsius. And you can see that the root mean square speed shifted over to the right, or it increased. Okay, so this is showing us and verifying from the kinetic molecular theory that as we increase the temperature, we're going to increase the kinetic energy and increase the speed of all of these molecules. So we can represent the total kinetic energy of 1 mole of a gas, and that's going to be equal to 3/2 R times the T. And remember that R is a constant, so our kinetic energy here is directly proportional to the temperature. We also know that our average kinetic energy of one molecule can be represented as 1/2 m times u squared, where u is the root mean square speed. So if we were going to set up a relationship between these two, we can say that 1/2 mu squared is going to equal 1 over Avogadro's number times 3/2 RT. And if we rearrange this particular expression, we can say that u squared, or the root mean squared, is going to equal to 3 times RT divided by Avogadro's number times m. Okay, this can be rearranged to say 3RT. If we have Avogadro's number times the mass, this is going to give us our molar mass. So the root mean square speed u, which we described above, can be calculated by taking 3 times R times T divided by the molar mass, all to the 1/2 power. So this gives us an equation to calculate our root mean square speed. And notice that as the molar mass increases and gets larger, our speed is going to decrease. So this is telling us, showing us that the larger the molecule is, the slower that it's going to move, or the lower the root mean square speed it's going to have.